DC in Baltimore, Dayton, Tennessee, and our newest facility in Denton, Texas. And with the obligatory company information put out, let's go ahead and get into the subject. Now, why cooling efficiency matters? Now, if we take a look at this graph right here, this was put out by the Lawrence Berkeley National Laboratory, and it's a prediction of the energy usage in data centers over the next 2.5 years. Currently, most people think that we're approximately at 5% of all the power that's being consumed within the United States. If you think about that, 5% of but that's not what's scary. What's scary is the lowest side of their prediction for 2028 is 6.7% of power. If it falls above that, which AI certainly can drive it there, the efficiency that we have to apply to keep the cooling power down relative to the IT power is going to become very critical to operations and to our operating expenses. What's driving this? Obviously, it's AI. If we take a look at the power usage required for AI, it's 10x what we would do with an old-style standard Google search. As I'm sure you know now today, it doesn't really matter. We're going to be talking a lot about CDUs and CDU efficiency. If you take a look at the thermal design power trend, the amount of power, the theoretical amount of power consumed by the chips themselves, we see that CPUs have been relatively linear. We haven't seen a real large increase in the TDP of the CPUs. But look what's happening to our GPUs. That trend is going to continue to grow. If you take a look at the GB200 super chips right now, we're looking at about 1.2 kW. If you look at the GB300 from NVIDIA, we're looking at about the cooling system of the data center. So I'm going to talk very specifically about CDUs, coolant distribution units. These are the heart of the liquid cooling, direct liquid to chip liquid cooling solutions. They come in many, many forms, outpacing the standardization of regulations and design and rating standards. So we're trying to apply standards to technology that right? Currently, we have no accepted test methodology that's recognized by a national ASHRAE. If you haven't heard of ASHRAE, it's the American Society of Heating, Refrigeration, and Air Conditioning Engineers, a very sexy organization. Posed a rating standard that I think makes sense, and I want to share it with you today. If we were to follow this proposal, we would be able to make apples to apples 127 committee. The 127 standard is the method of testing for rating for datacom cooling equipment. In it, we've pretty much agreed within the committee that these are the conditions we want to rate all CDUs at. Our FWS entering temperature of 26 degrees C, TCS supply of 30 degrees C, so we have a 4-degree approach temperature on the heat exchanger. A TCS return temperature of 39.6. If you don't know the efficiency of your equipment, it's very hard to determine what your operating expenses are going to be. If you do not know the efficiency of your equipment, you may not be able to meet the requirements of the energy efficiency standard that you are going to be applied to your data center, whether that be ASHRAE 90.4, energy efficiency for data center. And basically what I'm doing here, I have measured the heat transfer of the unit, I've subtracted the pump power out of the numerator. In the denominator, I have the measured CDU power. This comes directly off the power table in the test lab. And I'm proposing we put a calculated facility waterside pump power into it, recognizing that
comes with that. So a little bit of background on what EBM pouches. EBM pouches is air moving technology. Have high density bin structures for cooling the CPUs and GPUs, and in those compact solutions, it allows everybody to essentially give as much airflow in this big into a compact solution. It has our high density motor, electrical interfaces, has the as well as essentially redesigned the environment. it's not a traditional style axial fan. It's actually a little bit of a diagonal fan. So it's a hybrid style fan from axial and radial, and it's right in the center. Doing that, again, typically what's in racks and AI servers right now, there's a lot of single stage or multi-stage fans. In single stage axial fans, they provide you the airflow that you need. However, they don't provide you the static pressure fans. So it's two axial kind of back to back with an air straightener. Again, the first fan will essentially give you the airflow that you need. The second fan, or maybe the third fan in counter-rotating systems, will actually give you the static pressure of that you need to overcome essentially the cooling capacity of the server. The two-stage axial fans, the counter-rotating, and as well as diaforce. And if we would just simulate essentially an operating point that they can all essentially reach, you can see an actual reduction of audible noise to about 6 to 12 decibels already released to diaforce. So we have solutions essentially to integrate already into the AI servers. All three of our products, or all three of the products that we essentially have right now and to offer.
And of course, we have bigger aspects even. If we think of projects like Stargate, we were talking about 500 billion invested in AI infrastructures to come up with something like one single computer requiring 5 gigawatts of electricity.